Good evening. Here are yet again for another lovely session of CENG 3325 Structural Analysis. This is going to be part 2 of Lecture 3 of CENG 3325, and the main topic for this evening is risk. Risk and how we design for it. So, we learned a few things last time, and among these are some definitions of loads. So make sure we're recording, and we are, so we're good to go. So I want to talk about risk. Now, we learned a few things last time, and I think I'll review a bit of them here, just to start this video out. So we remember we saw a few things where we developed a system for classifying loads. Ways to classify loads. And we have a few ways of classifying loads. And 3 main ones. Now we could talk about live load, dead load, that sort of things. Those are types of loads. But more general, in terms of load classification, I define the following. I defined nominal loads. And nominal loads, again, these refer to the maximum expected load, expected value of a given type of load applied to a structure. Maximum value of a certain type of load expected to be applied to a structure. Applied to a structure. Now, it is important to keep in mind that these loads here, they do not have any kind of factoring, any kind of factor of safety. Nominal loads are basically your best guess of the actual real-world loads that are be applied to something. So these are the best guess of real values. Although, as engineers, we shouldn't use words like guess, we should use words like estimate. So in other words, if you estimate that from, say, a study of weather, that that you estimate the strongest hurricane load or hurricane wind that will ever be applied to a building is X number of miles per hour from a certain direction or something like that, if you take that load speed, or that wind speed, and calculate a force from it without applying any kind of factor of safety, any kind of extra above and beyond, that would be a nominal load. Ultimate load, so again, a best estimate of real values, and these have no accounting for risk. And we're going to talk about what I mean by accounting for risk in a bit. Then we have service loads, or serviceability loads. These are going to be your loads, your everyday loads. And there may be some factoring applied to these, but generally these are just your everyday loads. Typical loading. And we've already discussed this extensively, so I'm not going to worry too much about this. But what I really want to get at is your ultimate loading, because that's what we use a lot in strength design, and that's what we're going to spend most of our time this semester working with. Ultimate loads. These are the maximum design loads, what you're actually going to be designing your structure for. Again, assuming, although, again, serviceability, you'll often design this for elastic strength, that sort of thing, but these are the true maximum design loads, the ultimate loads. They're called ultimate loads for a reason. And what they fundamentally consider, though, is these loads will fundamentally have risk baked into them. To get nominal load, when we start with nominal loads, and applying various mathematical techniques, we will transform them into ultimate loads by considering risk. Ultimate loads have a mathematical estimate for risk baked into them. Risk baked into them. So let's start talking about risk. What do I mean when I say there is risk in loads? How does that make sense? What does that mean? So let's look at potential sources of risk. And to do that, I first need to ask, and I need to go back and ask, how do we get loads in the first place? Sources of risk in structures. Well, maybe I could start out by saying, what would be my zero risk design case? If I did not consider risk at all, how would this look? So for example, what would a zero risk case look like? What would zero risk consideration look like? Consideration look like? Well, consider this. What if I designed let's look at something simple. Let's look at a simple type of structure. Let's see, what could we do? Something relatively simple. We could do a building, but let's say, I think it might be better to start with something a little simpler, a little easier to understand, a little easier to comprehend, or a little easier example. Not to comprehend, but to describe. Okay, the same principles can be applied to any sort of structure. It can be as big as a building or a tall structure, or it can be something relatively simple. So what about something like this? What if I had something like here's a good one. What about a car lift? Let's consider a car lift. What I mean by a car lift would be a lifting or hoisting mechanism used at a mechanic shop to lift up a car. Let's say you had a car lift. Again, this would be a mechanic's car lift. So let's say I designed a mechanic's car lift without any consideration of risk. So maybe the car lift. We could think about what the car. Let's use a simple example. Maybe it's a big old single piston type of car lift where there's just a great big piston. Now, I don't know much about the design of car lifts, but let's just say there's a great big piston in the middle, and the car is going to be positioned on top of this, and I cannot draw cars to save my life, so it's going to look like a hat. Cars look like hats in my poor drawings. So, if I wanted to design a car lift, how might I do this? How would I consider this? Well, the first thing I would need to know is, how big is the car? Or what does it weigh? So what I would do is, I would probably go and say, I'd go to if I was tasked with designing one of these things, now imagine these things are mostly bought off the shelf, but if I had to design one of these things for some reason, I would go to the mechanic and say, okay, what is the typical car that you work on? And maybe I would design the lift, if I wasn't considering risk at all, maybe I design it for either the average car, or probably better would be like the biggest car the mechanic typically works on. So maybe I design the thing for a relatively large truck or a pickup truck or something like that. And so I design the thing for, I look up the weight, I find the weight of a big pickup truck, maybe the largest pickup truck. Literally, I just go to the mechanic and says, and ask, what is the biggest car you have worked on, or the heaviest car you've worked on in the last year? And I design the whole thing based upon that. And so I find the heaviest car, and that P, the load of that, becomes my point load P. Load of that is P. And then maybe I design it like this. I have a column in the center, and then I have a beam on top of it, basically a double cantilever beam. And I design it as such. I have a point load P over 2. Maybe I assume half of the load is over here, P over 2, P over 2, and then an upward load P here at the support. Well, that's all well and good, and so let's say I do this, and then based upon this, I size the beam using just mechanics. We could even just level mechanics and materials type knowledge. I size the beam based on bending and shear. So I design beam, this beam here for bending and shear, and I design a column based on compression. So, but when I do this, I don't consider any risk at all. I don't consider any variability. I don't consider any risk. So in other words, I've designed this as such. So in other words, if I calculate, for example, if I calculate the car tires, we'll apply a moment of X, apply a max bending moment of say M. I design that beam for exactly M. For exactly M. And again, this is not how you want to do things in the real world, but this is how you might design if you were not considering risk at all. So in other words, at that M, the stress in the beam, if we have our stress strain diagram here, stress strain diagram, then it goes yield plateau, then we get some strain hardening here. Our basically at that M, we're at the sigma ultimate. So I literally design it for ultimate. So when the car is on, when the heavy car, or the big truck in this case probably, is on lift, the bending stress is right at sigma ultimate. So in other words, the entire cross section will be fully engaged, and the beam will be at its maximum stress. Okay, and any other stress and will actually any higher stress, and this thing will actually fracture. Bending stress is at ultimate, is at maximum. And I do the same thing for shear and for the column. Same for shear and column. Same for shear and the column, or shear in beam and the column. In other words, I assume I'm going to take everything up to the maximum. In other words, therefore, at the critical case, the big heavy truck, my estimated maximum load, my maximum truck size for this lift, at the critical load, the members are fully loaded at really their ultimate load. 1 pound more, and this thing is coming down in multiple places. 1 pound more, and the column will buckle. 1 pound more, and the beam will fail in bending. That would be something that has zero risk, or zero consideration of risk. There would be quite a bit of risk, actually. And so, now, again, this is still engineering. It's not very good engineering, but it's still engineering. I'm not just choosing a size of a beam out of the air or pulling it out of my armpit. I'm looking at it and saying, okay, what is the heaviest thing I ever expect this? What is the heaviest truck the mechanic has ever had to lift up? And then designing everything at the limit. But what is wrong with this? The Bane problem, of course, with this kind of philosophy is risk. So what kind of risk can we have? Or where can this system go terribly wrong? So let's consider this. What are some sources of risk in this situation? What could go wrong? What could cause this to fail? So on one hand, it might seem like I did things fine, because after all, I literally said to the mechanic, I asked the mechanic, what is the biggest truck or biggest car or biggest van or biggest any vehicle that you will ever lift on this thing? And then I just designed it for that. You would think that would be fine. If it's strong enough for the biggest thing the mechanic will ever lift or ever has lifted, what could possibly go wrong? Well, let's find out. So again, as a review, or as a reminder, let me draw my little free body diagram here. Of this lift, we have P over 2, P over 2, and P. What could go wrong? Well, let's go down the list. The first and obvious one is the load is greater than P. Greater than P. Greater than P, than the assumed max. I should be more specific, or maybe more general. Load greater than the assumed max. So in other words, I decided, again, I went to the mechanic and said, "Oh, hey, what is the biggest car you've ever lifted into your shop, or you've ever treated or fixed up in your shop?" And the mechanic said, "Well, it was so and so and so and so," and I designed that for the dead weight of that car. But what about? Well, let's think of how that load might be exceeded. So the first obvious one would be, what if somebody just happens to roll into the shop with a car that's bigger than the one the mechanic has ever, or heavier than the one the mechanic has ever seen before. There's always a heavier car out there. Maybe maybe next year Ford comes out with a heavier model of some car, and then when that thing rolls on, when they try to lift that thing, it collapses down and kills the person standing underneath it. Or what if, for example, what if it's the exact same model? So, for example, maybe the heaviest car he ever lifted the mechanic ever works on is a certain type of big pickup truck. Well, what if in my assumption, I assumed that it was just the straight from the manufacturer, straight off the factory floor, straight off the car dealership, stock pickup truck. But then somebody rolls into the shop that's been heavily modified. Maybe there's a big attachment on the back of it. Maybe there's a big hitching mechanism. Maybe there's a big, camper type thing on the back, or any kind of bins and tool chests and things on there that add a couple 100 pounds. Or maybe there's just a bunch of crap in the bed of the truck. Maybe there's bricks in the back of the truck that for whatever reason the owner hadn't emptied out before he brought it into the shop. Maybe he was carrying a load of bricks and the car broke down and they had to tow the truck in, and they had to lift it up without taking the bricks out. And you might say, well, I'll just tell the mechanic to never lift anything heavier than this. Well, maybe eventually he sells the shop, and the person who comes along later didn't get the memo, and they think it's good for any truck or any car, and they end up taking it past the assumed load. 2, load distribution. Look what I assumed. I assumed a perfectly symmetrical case. In reality, vehicles don't really behave like that. You'll tend to have more weight near the front than the back. So if I were to properly assume this, I might assume like P over 3, and then 2P over 3 over here or something, or 2/3 P over here. But again, I would still always have some assumed load. So what if that's no longer true? What if I have a vehicle that the weight distribution is a little different? Maybe there's a bunch of weight in the back or more weight in the front. And again, if I go and concentrate all the load over here, suddenly the bending moment and shear are much higher over here. If I was already taking everything to the limit, then I would be exceeding that and causing failure. And in this case, since I was already assuming ultimate, failure would literally mean collapse, not just exceeding some stress. 3, what else? In terms of load distribution, another possibility was, what if I have a longer truck or a longer car? Somebody comes in, a manufacturer produces a longer vehicle, and then the bending moment arm is larger, etc., etc. What else? What about material? What if the steel? What about material properties? In other words, let's say I build this thing out of A36 steel. A36 steel has a minimum yield strength of 36 KSI. That's why it's A36 steel. And so it's a good bog standard and relatively affordable type of steel. It's been used for a very long time. So A36 will have a yield strength of 36 KSI. At least it will if it's up to spec. But there's always going to be some uncertainty. What if at the steel mill they screw up and the batch of steel that should be 36 KSI is actually 35 KSI? And it wouldn't have the ultimate stress would be higher than this. But let's say the ultimate stress is less than it should be. Maybe not even a lot. Maybe it's again, maybe the yield stress is supposed to be 36. Maybe it's 35, 34. That is pretty rare for it to happen, but it could happen. If I'm taking this thing up right to the limit of its stress, well, if that material has even the slightest imperfection of it, if it does not meet spec, well, suddenly this thing is going to fail. What about manufacturing defects? What if the person I hire to weld this up doesn't do, so if I was designing this, I would also prescribe welds. I would say I want a fillet weld or a full pen weld of this thickness and these locations of this length, that kind of thing. Well, what if the welder isn't very skilled, or maybe it's not their day, or maybe they make a mistake, and under the surface there are some defects that we can't see. You could have a weld, like a fillet weld. Say you have a plate here, and a plate here. And ideally, the way a fillet weld would work, this entire thing will be full. But just looking at it from the outside, your eye would be here, you'd be looking at it here. If there, you can only see the outer layer. What if there is a small cavity in here? So it's all filled in like it should be, except right at the root of the weld here, and there is a cavity. Looking at it from the outside, I would never be able to see that. And I would be counting on this weld giving me the full strength. But if I hadn't taken into account risk, if this structure will only work if the weld is built exactly as designed, I'm gonna have a problem. So we could have problems with welds, or there could actually be problems with the material itself, the members. What if so maybe these are W sections or something, small W sections. What if there is a defect in the W section? W sections are supposed, like any rolled steel shape, are supposed to have certain known sizes. What if there's a little imperfection somewhere in the middle of one, a little hole here, a little hole here? Maybe maybe an end of this got clipped at the factory, and there's a little bit of the end of the beam that's missing, and that would take out some of my bending moment capacity. So again, hopefully I could see some of these things, but you can have damage to things that you can't see just by looking at them. Now, there are tools you can use, some things called non-destructive evaluation, or non-destructive testing, where you say like X-ray things and that kind of stuff. But I'm pretty sure that I'm not going to be performing incredibly detailed X-ray analysis of a modest car jack or car lift, or a small-time mechanic or something. And then finally, maybe another source of risk would be age and deterioration and corrosion. Age, deterioration, and corrosion. Mechanic shops, now they're not the most damaging environments out there. They are, it's not like there's it's not like something like a offshore platform or something like that, where you have steel that's constantly exposed to salt air, that kind of thing. So it's not the worst environment out there, but it's still if you think of a mechanic shop, it's it's going to be it's definitely not the most ideal environment either, though. Whenever the doors to the mechanic's garage open up, outsider will come rushing in, and so this thing it's not going to be in the rain, but it's still going to be exposed to hot and cold, varying temperature cycles, age, things like that. And every steel, just like anything else, is going to slowly corrode. It's going to slowly rust. It's going to slowly deteriorate, etc. Now, we can mitigate that. We can paint it. We can maintain it. We can inspect it, etc. But you cannot resist the forces of time. So, even if all the shapes are all up to par, even if the material is up to par, even if everything is built 100% correctly, well, a big piece of equipment like this, especially if something an engineer is designing, a structural or mechanical engineer is designing, this thing is probably going to sit in that shop for many years. I mean, it might be there for decades, for however long that shop is operational. So while it's okay today, is it going to be okay 20 years from now? That's another story. So the way you often handle this in certain applications is you might, sometimes when designing things for corrosive environments, you'll actually assume a sort of corrosion case where you will make sure your structure is still sound, even if it's lost, say, the outer 1/16 of an inch of its surface area due to corrosion. Now that's probably excessive for this sort of thing, but if I design my structure already to the maximum limits right from the very beginning, if I have any kind of corrosion or even damage, this damage could be chemical, like corrosion, or it could be physical. Like, for example, this is a auto body shop, or not, this is a mechanic shop. So, there's going to be people carrying tools around, there's going to be cars moving around. What happens if at some point, when this thing is half up, they try to roll a car onto it, and it gets whacked, and it's off kilter a little bit, and it's bent a little bit? Well, now I have mechanical damage, and that mechanical damage could cause the thing to collapse under a critical loading. So anyway, the point being, there are I could sit here all night and do this. There are an almost endless sources of potential risk. And so basically, in summary, therefore, there are an almost endless sources of risk. An almost endless lists of risk. Almost endless a list of risks. But they do generally fall into two categories. And this will be important later on. One, the load is larger than we expected. And that would, 1 and 2 would fall into that. And 2, our structure is not as strong as we assumed. This could be due to material, or it could be to construction defects, or to age, etc. Structure is not as strong as assumed. Or I should say not as assumed, as designed. As initially designed. So I need it to hold 10,000 pounds. It's only actually able to hold 8,000 pounds, etc. As initially designed. So we have risk. All of these are risks. And engineers can be good at estimating risks, but engineers, like structural engineers, like any type of engineer, now we can do things there are all sorts of ways to hopefully adequately and accurately estimate risks. But we are not prophets. We do not see the future. We can never completely know what's going to happen. And you can reduce some of these risks. So like I mentioned, you could do non-destructive evaluation. You could, if I wanted to make sure I had really good steel, I could make it. If I wanted to make sure I absolutely minimize the chance of having material property problems, I could make sure to buy from a highly reputable steel mill and made sure they double checked and triple checked their batches and everything else. I could actually run some material tests of my own. I could take samples of the material and test it in a strength testing machine, in a tensile tester, in a shear tester, whatever. But no matter what I do, there's still going to be some risk because, I could take a sample of the steel and test it, but who's to say that maybe the piece I tested happened to be stronger, maybe the defect was elsewhere in the batch that was poured or something like that. Anyway, the moral of this is that while risk can be controlled and reduced, it can never be eliminated. Can be controlled and reduced. It can never be eliminated. Ever be eliminated. And this is why we have nominal versus ultimate loads. Again, nominal loads. Nominal loads, an example of a nominal load would be this P over 2. That is my best guess of the heaviest load of a certain type this thing will ever encounter. But I haven't considered any risk into that number. Again, this is just the best estimate. The best estimate for the highest load of a certain type. Of a certain type. And ultimate loads are nominal loads adjusted for risk. So just another way of stating this. Are nominal loads combined and adjusted for risk. So we need to talk about how we're going to do this. How are we going to transform these nominal loads into ultimate loads? Nominal loads combined and adjusted for risk. Okay. And so there are two main governing philosophies that we use in structural engineering. And both of them have certain merits, but we'll discuss each of these. So maybe I could call this risk management philosophies. And this would be ASD versus LRFD. ASD versus LRFD. So I haven't described what those are yet, but we will do this now. So let us first consider, let me just maybe put some subheadings here. LRFD. Let's talk about let's do ASD first. So we have ASD. Actually, let's write this out and then put the abbreviation. ASD stands for Allowable Stress Design. Allowable Stress Design, ASD. And then you have LRFD, which is Load Resistance Factor Design. Quite the mouthful. Load Resistance Factor Design, LRFD. LRFD. Load Resistance Factor Design, LRFD. So, what do these mean? Well, you've named them, but what do these actually mean? Well, it's kind of in the name, but we can, if you know what all these words are and you can parse all of them and think through their combinations, well, it's kind of in the name, but I'd like to give a little bit more explanation. Allowable stress design effectively uses a single factor or number. Or number to account for risk. And this is more traditional. It's what's been used for a long time. This is actually almost ancient, although mathematically it's probably been used since the 1800s. It's more traditional. But in fact, the main term that you hear, it's been used for so long that the technical term is actually, this is one example, one of the few examples of it where a technical term has actually sort of penetrated the public consciousness or become a common phrase. And that phrase is factor of safety. So for example, if you have a factor of safety of 2, back to that example of the lift, with a factor of safety equal to 2, I would design that lift for a load of 2p instead of simply p. I would double the load and then design my members accordingly. I would design a lift for 2p, twice the point load. I would double it. And basically this uses one single factor to take into account all of this, to take into account all of our uncertainty. Load resistance factor design, however, we use, notice the words, load resistance factor design. Here, separate multipliers are applied to the loads and the resistance depending on level of uncertainty of each. So I want to further talk about this more in detail. I wanted to define both of these on the same page. Separate multipliers are applied to loads and resistances depending on the level of uncertainty in each. On the statistical uncertainty for each. So here, this is more modern. This kind of thing was really developed in the 1970s, 1980s, and started really being employed in codes in the 1990s, 2000s, etc. But that's a simplification. But anyway, but this is more generally considered more scientific. Wow. This is generally considered more scientific, and it's a more modern approach. But all of the new codes, all of the recent codes in the last 10 years have had LRFD approaches baked into them. So if you're designing steel, you'll be using the ASD steel manual. It is it's mainly entirely based on LRFD now. Same thing with the ACI concrete manual. All of these now employ LRFD. But first, I want to talk about the simpler one, the one that's a little easier to understand, and that's allowable stress design. So let's consider allowable stress design. So how might we consider this? Well, or how might we apply this? Well, for example, consider something like this. Let's say if I have a simple rod that I'm going to pull on with a force, a nominal load of, say, 10 kips. 10 kips. 10 kips. Now let's see, or let's say I'm going to pull out with a force P. Let's keep it a little bit simpler than that. Let's look at it in terms of stress rather than just load. Let's say it's made of A36 steel, and my limit step. I'm going to say I want to limit things to the elastic stress. I do not want to. I want the elastic stress to be my limit. And let's say it has an area of, I don't know, cross-sectional area. Let's put 1 square inch. Keep it relatively simple. A equals 1 inch squared. And so let's say I want to use a factor of safety equal to, I don't know, let's say 1.2. A factor of safety of 1.2. What load P can I safely apply? Well, how you use the factor of safety is if you're calculating allowable stress, you would apply, when calculating allowable stress, you would divide by the factor of safety, because that would basically say, I'm not going to allow myself to go fully up to the elastic stress. So when calculating a stress, an allowable stress, or I should probably say when calculating a supply, divide by factor of safety. When calculating a demand, we multiply by the factor of safety. A demand, a load, for example, or a required stress, we multiply by factor of safety. These two things are essentially the same. So, for example, I could use the expression sigma ultimate here for the maximum factored ultimate stress, or sorry, for the maximum ultimate stress on this thing. And I know that sigma ultimate, in this case, would have to be less than or equal to sigma yield divided by the factor of safety. And here, the ultimate stress would be P divided by 1 inch squared. And then this would have to be less than 36 KSI divided by 1.2. So I'll throw that into a calculator really quick. 36 over 1.2. 36 over 1.2. And this comes to, oh, I should have done that in my head. This comes to 30 KSI. And then I have P over 1 inch squared is less than or equal to 30 KSI, which then means that P must be less than or equal to 30 kips. So basically, with this factor of safety of 1.2, even though the material's yield stress is 36, I'm going to say I'm not going to allow it to exceed 30 KSI. And the point of that is to take into account uncertainty. So if the load is larger than I thought, if the steel is not as strong as I thought, if there's corrosion damage, etc., hopefully this will take care of it. So again, the whole idea with this is that we are only using a single number. Only using a single number. A single number. So we're only using a single number. Uncertainty in loads and risk are baked in, uncertainties of loads and structural strength are all baked into these. Are all lumped together. Now, that doesn't mean this is just completely blind. In codes that do use ASD or previously used ASD, and you can actually still find some ASD. You actually can design any steel structure, for example, still using the ASD provisions if you want. ASD design is not unsafe. If you design things using ASD approaches, ASD codes and such, you're going to end up with a structure that's actually perfectly safe. What we often end up with is you still have a safe structure. It's not going to fail. It's not going to collapse. But what tends to happen is, at least on average compared to LRFD, theoretically at least, you end up with something that ends up being heavier than it needs to be, and ends up being more inefficient than it otherwise could be. So ASD does not result in unsafe structures. Rather, it usually ends up with structures that are over-designed a bit. But the question is, though, one thing to keep in mind, or one thing I want to mention, is that the factors of safety are not constant across all applications. Are not constant across all applications. And what I mean by this is that what factor of safety you're going to use, the factor of safety will be chosen, usually by code, will be chosen based on a few things. One, member type. Two, maybe the load type. And three, the, well, maybe not load type, you don't see that as often, but especially member type, and two, the importance of the member. Importance of member or structure, even more commonly structure. Importance of structure, and three, let's see, consequences of failure is probably a better way of saying this. So for example, member types. Some members are just by their nature more variable than others, and also type of loading. So, for example, columns in compression, you'd want to use a higher factor of safety than, say, a tension member. Just because compression, because of buckling and things like that, it's always going to be a little bit more unpredictable than tension. Same thing with so that would be same thing with depending on the type of members, etc., etc. Also, types of members. You might use a higher factor of safety for a column than a beam, and the reason for that is if one beam fails, often it'll just be able to shed load to an adjacent beam. But if a column fails, an entire series of beams are going to fall over, and well, that's going to be a much bigger issue because a single column supports many beams. So the failure of that column, and at least the fracture of that column, is much more is much more catastrophic than a failure of a single beam. Importance of structure. This is an interesting one. Or the structure type. If I'm going down the road, if I see I can actually, if you get an eye for this, you can often tell what a building was designed for, what its intended use is, just by looking at it. So, for example, if you are the design codes, the building code, that sort of thing, has something that's referred to as the importance factor of a structure. So, there are some buildings, maybe I'll even mention this over here. Importance factor is a factor of safety that can be applied to loads based on the type of structure. That usually just increase loads. That increases loads based on the type of structure. So in other words, you could have 3 buildings next door to each other. Imagine you had 3 buildings next door to each other. One was a single family house. Just a nice, happy single family house. Just nice and simple. Looks like a wizard hat or something. Looks like a mountain. Anyway, so nice, just basic single family house. Then maybe over here you had like a storage building, or maybe like a shed or something. Maybe it could be a workshop or a shed. Let's just say it's a shed. Shed back here. And then over here you have a great big hospital. And let's say this is in Houston, so we don't have zoning, so we'll just go ahead and put things wherever we want. So we have our nice little Red Cross kind of emblem on here for the hospital. Now these are going to be literally right next door to each other. Maybe a little helipad on top or something. Anyway, so these are right next door to each other. So what that means is they're going to be exposed to the exact same environmental conditions. They're all going to be subject to the same wind, more or less, unless we consider shielding. I guess this one would also have elevation to take into account. The higher up you go, the higher wind speeds, etc. But in general, these will have the same loads. So same loading types, same environmental conditions. They're going to have the same types of rain load applied, the same snow, same everything else. If it's snowing on this one, it's snowing on this one. If the wind's blowing on this one, it's blowing on this one. Same environmental conditions. But these have different importances. If the shed falls over, who cares? Not same importance though. So you might, for an importance factor, you might actually multiply your loads by something like 0.8 for the shed. You might do your best estimate to calculate the loads on the thing, and you then might actually reduce those a little bit and cheat a little bit because, you know what, this is a shed. It's a machine shed. It's a tool shed. It's something that's just meant to store stuff. Nobody lives in there. Nobody spends all day working in there. Nobody sleeps in there. If that thing falls over during a hurricane, I mean, yeah, you might lose some power tools or something, and that would be, if you didn't have insurance or something, or it was your favorite old saw or something like that, I suppose you could have some minor emotional damage. But primarily, if this thing falls over, the only damage is going to be economic. Nobody's going to get injured. Nobody's going to nobody's going to die if this thing falls over. Unless for some reason a big earthquake hits right at the one instant you happen to be in there getting the garden hose. But what are the odds of that are very infrequent. So you might have something like a 0.8 for this. Maybe that's an importance factor that you're going to bake into your factor of safety. Single family house, you might use something like 1.0. That Now, if the house falls in on you while you're in it, yes, that's going to be, you don't want that to happen. I don't want that to happen to my house. But if it does, I don't want to say that's not important. It absolutely is. If someone's house falls in on them, the roof falls in on them. But in terms of consequences, broad consequences, if a single family house collapses, the worst consequence is that one family inside perishes. And that's extremely unfortunate. But like everything else, we have to balance protection versus cost, like we discussed previously. If we want to, we could massively overdesign your house, but then you probably couldn't be able to afford to live in there in the first place. But something like this, a big public building like a hospital, we might use a very large importance factor, like 1.5 or even 2.0. And so, because of this, these things, maybe I'll estimate that it'll have a wind load of X, and then we'll actually go and design it for a wind load of 2X, just based on importance factor. And the reason for this is that these big public buildings, and these things include things like very high importance buildings, some examples of these would be things like hospitals, police and fire stations, and interestingly enough, public schools, school buildings. Now, not just because we don't want to have buildings fall in and... Okay, so let's back up this. The whole idea is that during your really big event, your extreme environmental events, these are the last buildings you want to ever collapse. And this makes sense. Like if you have the great big hurricane, the great big earthquake, if you're here in Houston, that the big event would be the big hurricane. Hurricane Harvey, but probably something with even stronger winds. Hurricane Harvey had immense rainfall, but it was not the critical wind that you can have with hurricanes. Out in somewhere on the west coast, like California, the critical loading, environmental loading, would be the cliche, the big one, the great big earthquake. That'd be your critical environmental loading. But in these kind of extreme events, they don't just damage one structure, they can damage every building in a city. And so, if you get especially like earthquake, hurricane, these don't just touch down on one area and damage one building. It's not like a fire or something. They apply to everything in the community all at once. And so, if you have a earthquake, if you have a big hurricane, these, especially I'll talk about the schools in a bit, but especially the hospitals, police, and fire, this is the last thing I ever want to fall over. This is the last thing in the world I want to collapse. If there is a big environmental event like a huge storm or earthquake that goes and levels everything in the town, if I could pick one building or one set of buildings that are going to be still standing, I want it to be the hospitals, the police station. I want it to be the hospital, the police station, and the fire station. The hospitals, because once we had all those buildings fall over, well, we got to be able to take those injured people somewhere. Police, you need to be able to maintain order at times of chaos during natural calamities. Fire, if there's any kind of fire from gas mains leaking, that sort of thing. And public school buildings, this is an interesting one. I'm not sure if you're familiar with this, but if you've seen things like this, whenever you hear on the news of a big emergency, people tend to evacuate to school buildings. And the reason for this, especially in smaller communities, they may be the only building around that is large enough to hold large numbers of people in the event of a large number of homes being destroyed. And actually there's one particular area of school buildings that's designed usually stronger than anything else, and that's often a school gym, especially high school and middle school gyms. And the reason for that is, well, think about it. If you need a emergency evacuation shelter, this is already so. For example, it's usually not practical for a community to invest in a building that is nothing but a emergency evacuation shelter. That would be for something that you only need to use every 10 years or 5 years. It really isn't practical to build something and pay to build it and pay to maintain it and pay to keep it, the lights on, water running, and everything else, for something that you're only going to use once every 10 years. That really doesn't make much sense. However, think of a middle school or a high school, especially. If you're going to need to, if a bunch of homes are destroyed and those people need an emergency evacuation shelter, what are you going to need? You're going to need space to put them. You're going to need a place to prepare meals, and you're going to need a place where they can shower, shave, all that kind of toiletry stuff. Use the facilities, use the bathroom, all that kind of stuff. Well, A high school or middle school, they have that in abundance. There is that you can set up cots in the school gym, and all of the people can sleep in bunk beds there or in classrooms. They can shower in the showers that are normally used for sports teams and for gym class, and they can have meals prepared or served right in the cafeteria that already exists on campus anyway. Schools often are built to serve a sort of dual function. Yes, their primary purpose is always going to be for education, but one of their secondary purposes is community emergency response. The public schools are used for this. Because of that, when we design school buildings, we tend to really over-design them just because of their importance. So not only is it important that a school building doesn't fall over and kill children, but that's obviously important, but they are also the sort of default public evacuation place in the event of homes being destroyed by natural disasters. Anyway, all of these are sorts of things that will be baked into the factor of safety in an ASD system. And finally, also consequences of failure. We talked about this a bit with beams versus columns, but one area where you see this, where I've seen this a lot, where you have very high factors of safety, are in, say, lifting mechanisms. So if you have a lifting mechanism, so for example, let's say you need to lift something heavy on a construction site, or if you're a equipment supplier that sells like pad eyes, or lifting hoists and wire rope and this sort of thing. So a pad eye is something like this. It's where you can maybe have this attached to a beam here, maybe a flange here, wide flange, something like that. And this would be welded on. And then there would be a bolt going through here. And if you looked at it from the side, there might be something like this. If you look at this thing from the side, now there could be different variations of this. But if you looked at just this piece from the side, or maybe I can include the beam as well, it would look something like this. If you looked at it from the side, maybe it would look something like this. And then a bolt would be passed through here, and then this could be lifted up, and you could lift it with a crane or with a crane would be a good example. Any kind of lifting mechanism. Lifting devices, lifting mechanisms always have huge factors of safety. And the reason is because of the consequence of failure. Again, it all comes down to consequences of failure. If you are lifting a heavy load on a construction site, if that cable snaps, if that lift fails, if that thing falls, you could potentially have great big heavy objects falling from great heights. Same things like elevators are another example. An elevator might have a dozen different cables, and you might only need one of them to actually function properly to hold the elevator up. You might have super redundancy on the cables that hold elevators up. That's very common. So you might have 8 cables and 7 of them could snap, and as long as one was still fine, the elevator wouldn't fall. Again, it's because of the consequences of failure. Lifting mechanisms are things that are really what we call single points of failure. Lifting tend to be single points of failure. Often, especially things like pad eyes. Normally in structures, there's a great deal of redundancy. So if one member fails, load can be passed on to another one. You might get yielding damage and excessive deformation, but usually you can avoid collapse just by spread of load. But when you're lifting something, often you're supporting it by a single point, a single object, and so if that fails, the entire thing's coming down, and also, as it falls, it gains an enormous amount of kinetic energy, which means the damage can be much, much higher to anything underneath it, whether it be a part of another building, a person, God forbid, an automobile, whatever it may be. So lifts tend to have very large factors of safety purely because of the consequences of failure. Okay, next, let's consider, so that covers allowable stress design. Let's next consider load resistance factor design. Load resistance factor design. Actually, let me see what color I used here. There we go. All the same for consistency. So LRFD, load resistance factor design. Load resistance factor design. LRFD. So what does this mean? Well, I mentioned this was the more scientific approach, and what I mean by that is it's usually these are chosen from a great deal of historical studies and laboratory studies. So, again, we're going to be apply factors to both loads and resistance independently. Again, loads are your actual demand, and your resistance is the strength of the structure. Loads and resistance separately. To loads and resistance separately. So, anyway, and these are, so you're applying these separately, you're applying factors to loads and resistance separately, and basically you're going to have a load factor. These will increase nominal loads. And resistance factors decrease nominal resistance. So again, nominal resistance, just like nominal load, nominal means the best estimate without any kind of risk adjustment. Resistance factor, a resistance factor will decrease the nominal resistance. It'll decrease the nominal resistance. And so what you'll have is something like this. You may have phi. Let me write this in general form. Let me write a generic form of our LRFD philosophy. So we would have something like phi, P nominal, is less than or equal to, let's say, I don't know, gamma R nominal. Something like that. We could choose different variables, but this would be the general form. Phi would be a load factor. And this again will be greater than 1. Pn, P sub n, that's a subscript if you can't tell, or now it's gone. Pn would be the nominal load. Gamma, now we don't usually use these variables explicitly like this, we tend to just write things out. Gamma would be the resistance factor. And Rn would be the nominal resistance. So we're using two independent factors. So let us consider, let's run through a very similar example to the other one. Let's do the exact same thing. I have let's say a load, the same thing, a P here and a P here. And again, it's A36 steel with an area, cross-sectional area, equal to 1 inch squared. Equal to 1 inch squared. And based on, I'm going to assume, let's assume, for this case, assume a load factor of, let's say, 0.9. That'd be pretty good for tension. And a resistance factor, actually not, sorry, load factor. Let's do that needs to be greater than 1. Did I mention this one is less than 1? Sorry, this resistance factor needs to be less than 1 here. Less than 1. And so assume a load factor of, I don't know, 1.2, for example, and a resistance factor of 0.9. And let's say I then go and ask, okay, what was loaded this other one had? Let's base it off of that. Let's say I need this rod to carry a load, a tensile load of 30 kips. Is it adequate? 30 kips. Is it adequate? And it will be adequate if the previous equation I wrote, or sorry, not equation, inequality I wrote, remains true. So let's calculate all this. Or first we can just say, okay, well, P nominal, that's going to be the nominal load. So let's say this is 30 kips. That's what that was given, 30 kips. Then let's say the load factor, our phi, let's say this is, well, not just let's say, it is 1.2. So again, this is meant to take into account variability in the loads. So based on my best estimates, or based on my experience, statistical analysis, etc., I see that for this type of load member and this type of loading, a variability of load of 20% is typical within a certain number of standard deviations, etc. And so then, in turn, I can get phi RN, or phi PN. This is going to be 30 times 1.2, and that will come to 36, I believe, if I can math correctly. Yes, 36 kips. Oh, not KSI, kips. Then, so we have our phi PN. Then, our nominal resistance, well, this is just going to be the A36 steel, the yield stress, 36 KSI, times 1 inch squared. And so that comes to 36 kips. 36 kips. But then phi RN is going to be 0.9 times 36, and that would be 32. 32.4. I apparently can't math correctly. It's a little late at night. That would be 32.4 kips. So is my equation true? Or my inequality? Again, phi PN must be greater, or must be less than or equal to, let's say, gamma RN. In other words, factored load must be less than factored resistance. This is what I need. This is what I'm allowed to have. Demand and supply. And is this true? Well, 36 less than or equal to 32.4. Nope. No good. Inadequate. I would need to redesign. We are no good. Now, must redesign. Now note, this does not mean that this thing's going to fail. By definition, this is another definition of failure. So this doesn't mean that this thing is going to immediately collapse, but notice what we had. This thing's nominal resistance, it's right at the yield stress, without any consideration of risk, is 36 kips. The expected load, my best estimate for the load, unfactored, is 30 kips. So 30 is less than 36. Based on nominal capacity alone, this would be fine. But when we start taking into account risk, then we can see that this would not pass a risk-based approach, or a risk-based check. So yes, it's probably going to be fine, but when considering all the potential sources of risk that we saw previously and others, this would not be safe, because again, as long as everything is fine, as long as everything is expected, it'll be fine, but if it's not, it may not be fine, or things could go very badly very quickly. So the question is, the next question is determining load and resistance factors. Now, I was being a bit disingenuous on the previous problem. Generally, you don't apply resistance factors as a single thing like that, or sorry, load factors as a single number like that. Typically, you use load combinations, which is something we'll be talking about shortly. So, determining load and resistance factors. Well, thankfully for y'all students, this is not something you're going to have to do in this class. You're going to have to be applying load and resistance factors, but you're not going to determine them. Load and resistance factors come from a few places. Come from basically studies. Come from scientific study. So for example, load factors. What might you do if you want to estimate the variability of a load factor? What you would do is you would do something like, okay, for example, consider live load. Maybe you are designing a room or a building for 100 PSF live load, even live load, etc. But through a series of studies, people have gone and actually, maybe that's the standard assumption, but then you do a study by you go to a bunch of buildings of the similar type that are designed for that type of loading, and you look around those and count, okay, well, let's say you're designing a school building and you're assuming classrooms have to carry X amount of load. What you might do is you might go out and do a survey of thousands of classrooms at random times and ask, okay, how often is our assumed live load, is the actual live load, in other words, the total combined mass or weight of all of the students in the classroom, the teacher, the desks, the chairs, the tables, all that kind of stuff, maybe even interior wall partitions. How often is that more than our assumed load, and by how much? So in other words, you're doing a statistical analysis of how variable a load is. And so basically on this, some loads are more intrinsically variable than others. Something like dead load of a structure, that's going to have a very low relatively low load factor, and that's because when you build a structure, you generally know the weight of it. Something like earthquake load may have much higher load factors, because you intrinsically just don't know what that's going to be ahead of time. So usually these are done through grants. University faculty members and industry researchers will go and perform a whole bunch of studies and say, okay, well, what is the variability of this type of loading? What's the variability of this type of loading? Maybe Houston, we never assume snow, but what is the actual chance per year of snow happening? And what do we have to multiply our assumed snow load in Houston or anywhere else by? So these are done, again, by statistical analysis and scientific study, analyzing how often loads assume nominal loads and by how much. How often actual environmental loads, or actual loads, I should say actual real world loads, actual real world loads exceed best estimated loads, and by how much. And by how much. And so the more variable, the more variable load, the higher the load factor. We're gonna make it bigger effectively. The more the load, the variation, the higher the load factor. So for example, if I had different types of loading, maybe this is my median, X bar or something like that, or my mean, let me draw two different types of load spread. So this is my average load. This is just a qualitative graph here. Maybe for something like this, let me contrast this with another color first, another curve. Here, Christmas colors. Okay, so we can see that, actually let me draw this as intersecting this one here. That'll be even nicer. So both of these loads have the same average expected value. However, this one is more variable. So green is more variable. The green is more variable. Has more spread. So they have the same average expected value. Same average value. But green is more varied. It has a higher standard of deviation and variance. but green, more unpredictable. Unpredictable, or more variable. Dictable. So maybe for this one you might use maybe for this one we would use a load factor of 1.2. And for this one you might use a load factor of 1.6. Just to make sure that again, the higher the variability, the larger the standard deviation, the more you're going to need, the higher the load factor you're going to need. And again, that takes into account uncertainty in the load, uncertainty in environmental conditions, that sort of thing. Next, I want to talk about resistance factors. How do you determine these? And again, when you actually design this stuff using this, you don't have to do these analyses yourself. You don't have to go and count a bunch of classrooms. You don't have to go and, in terms of loading, you don't have to go and, for wind load, you don't have to go and measure a bunch of winds and things like that whenever you're designing a building. But over the decades, as LRFD has been developed, again, researchers in both academia and industry have done these types of studies. They'll get grants. They've got grants. They make a research proposal, something like, I want to investigate the variability of seismic loading, and then they do that. They gather a bunch of data and see what kind of spread exists on that, and then do some statistical analysis to see what kind of factors, what kind of load factor we would need to take into account for that variability. And so again, you don't have to perform these analyses yourself. However, all of these are baked into the load factors that we see in the codes. Now, resistance factors, how do you determine this? It's very simple, very similar. Again, resistance factors account for variations, unpredictable variations in strength. In strength and capacity. And these are found also through primarily through laboratory exercises, actually laboratory experiments. These are determined experimentally, usually. Again, the goal, figure out how variable, or the spread, or how variable a member's strength is. A type of member's strengths will be. Type of member strength is. Strength is. So, and how would you do this? Well, let's say I was interested in finding out the variability of, say, W sections, like a wide flange shape, in bending. Well, if I wanted to know how variable the capacity of these things are, maybe I would probably want to go and get a whole bunch of the same beam size, and then predict, basically using the equations of mechanics, predict what the capacity of this thing is. And then what I would do is I would get a whole bunch of those straight from the manufacturer, or if I wanted to investigate corrosion, I might pull some old ones out of buildings that are being torn down or something, and I would just break them. I would put them in. I would get a whole bunch of these W sections of the same type and compare, and basically do a whole bunch of, I load them up until they fail, and then I just go and say, okay, well, maybe this is the average, and then here, but then some are going to be, it turns out, will have less than was expected. Some will have more than what's expected. And what is that range? And so different types of members or members in different types of loadings will have different resistance factors on them. And again, these are all going to be less than 1. So for example, for a beam, you might use, or a tension member, a steel tension member, where there's less intrinsic variability, you might use a resistance factor. I've been using gamma previously. I might say gamma is equal to 0.9, less variable. Something like a column, though, you might use a gamma equal to 0.75. Here we're going to allow ourselves to take up to 90% of what we feel a tension member could take. Here you're only going to go up to 75%. And that's just because some member types and certain types of loading are just statistically more variable than the next. And so how do these combine together? Resistance factors and load factors statistics, or statistical approach. And load factors. So let us consider a plot here. Let's say we have, I'll do one curve for supply and one curve for demand, or one curve for loads, the other for resistance. So let's say I have one bell curve. And this is load. And another bell curve that will be resistance. As we already know, we'll never be able to exactly know the maximum loads a structure will encounter. We can estimate it with the best of our ability, but we can never know 100%. So in other words, so when we multiply these things, when we apply a factor, this is maybe load, or sorry, this would be something like in KIPS, KSI, something like that, some sort of unit of force or stress, KSI, KIPS, etc. Basically, when we apply a load factor, we tend to, we're trying to take into account the overlap. We're trying to take into account the spread of it. And so if we design our, we start with our loads and we multiply by a load factor, basically we'll end up with something that is hopefully well beyond the curve of the load. But anyway, even with that, even no matter what we do though, this is important to keep in mind. There is always going to be some overlap. These things have tails that asymptotically approach zero. They never actually reach zero. So that overlap, well, think about here. If you're in this region, you don't have a problem. Again, because you don't have a problem. Well, actually, you do have a problem. Let's think about this. Here, as long as our resistance is greater than our load, you're going to be fine. But in this overlap region here, that is where you get failure. You get it where in a case where for a certain loading or for a certain value, here actually should be, this should probably label this wrong, sorry about that. This should be KSI, KIPS, etc. KIPS, etc. And is that right? Let me think about this. Let's see. Again, the overlap is going to be where you have failure. Oh no, sorry. This should be. I'm confusing myself a little late at night. KSI, KIPS, here, and this would be the frequency. It's a frequency plot. So how many, based on a random sampling of loads, how many of them will be here? How many will be here? How many will be here? If you're way down here, if you're over here in the curve, you're going to be fine because your load is much less than expected. You're going to be fine. If you're over here in this part of the curve, so let me label these maybe something like region 1, 2, and 3. In region 1, load is less than estimated. No problem. You're good. You're fine. 2, resistance is greater than estimated. Resistance greater than estimated. So we're good. But in zone 3, the overlapping range, this is failure. Because at this point, look here, you have the load is going to be further to the right than the resistance. So here you have failure. Load is greater than resistance. So basically what happens is when you apply a resistance factor, you're effectively shifting this thing to the right. So you're decreasing the size of this overlap zone because you're making your members stronger than they would otherwise be. So, but our goal as engineers is to make this thing as small as possible. However, that it is impossible to eliminate the overlap region. Completely impossible to eliminate this overlap region. There are always going to be some cases where failure is possible. Some failure is always possible. This is what comes back down to there can always be a greater load. There can always be a greater form of load, or a greater value of load. You know, maybe you design even if you design your building for the great big earthquake, well, maybe a bigger one that's never been recorded. Maybe an exceptionally large one, bigger than the biggest one ever seen, hits. There's always a small chance of that. Same thing. Maybe if you could design a building for a very high live load, but maybe some crazy person buys the building and then starts using it to hold lead bricks or something like that. That's very unlikely, but it could happen. So some form of risk is always going to be there. Risk of failure, not necessarily collapse. Collapse and failure are not the same thing. Failure will always exist. A stronger structure, making the structure stronger, will reduce this risk or lower that overlap. Shrinks the region where the load and resistance, where a load exceeds resistance. Surpasses, I should say. Surpasses resistance, but that region can never be eliminated. Even if you literally did decide to design your building or house or office building, whatever it is, like a bunker, and even if you were willing to live in it and work in it, you still couldn't eliminate all risk, because there's one load type that we haven't discussed and we don't usually design something for, and that would be load case M. If someone ever tells me they can design a structure for any and all loadings, they're just going to be really conservative, and this structure will always be able to withstand any load whatsoever, I bring up load case M, and that would be the very ridiculous meteor loading. And, this risk is very small, but it is actually very real. At any given moment, at any given time of day, a great big rock could fall out of the sky and land right on your head. A great big rock could fall in the sky and land right in your house, completely destroying it. And there would be basically nothing you could do to prevent that. No matter how strong you built that building, there's always a chance. There's always a big enough rock that could fall out of the sky and destroy it. Now, so we don't literally design buildings for this. You'll never see meteor loading in ASC 7 or something like that. But it is a fun example of how it is a fun example I like to use of how you can never eliminate risk entirely. So you can never eliminate risk entirely. Let's see. So we have that covered. You can never have 0% failure or 0% risk of failure. But finally, I might look at how we actually calculate, how we actually go about calculating your sort of factored loading. In the previous example, maybe I'll put a header on this. Factored loading. Factoring loads. Here. Factoring loads. So here, let's see, where was that example? Back here, we just use a single load factor. That's typically not done, though. Typically, we deal with load combinations. We typically do not apply load factors to just a single load and then design for that single load. Typically do not apply factors to a single load and just design for it. I should say, do not design for a single load and a single load factor. A single load and a single load factor. Load factor. Rather, we use load combinations. And the reason for this is that if you don't use load combinations, you're going to end up with a structure that's ridiculously strong and ridiculously overly built, which is not economical and is really can be as bad as under-designing a structure in terms of an engineer doing their job. So here, the whole idea of this is looking at statistically, and these combinations do come from statistical analyses. A lot of scientific research, published papers, etc. Scientific literature or scientific studies. And the reason we don't, now you might think we could just say, oh, why don't we just add up all the loads, add up all the types of loads and just multiply by one resistance factor? Well, the reason for that is that for any given type of load, it is very unlikely that it would all be applied simultaneously. So for example, consider our school building. The critical live load case for a classroom, I would think something like, imagine we had a guest speaker come in, some famous guest speaker. Maybe you have a large gathering. So we might imagine we brought in some really famous guest speaker, and I was going to have some famous structural engineer or architect or something like that speaking in front of my structural engineering class, and I advertised it, and I let students who aren't even in my class but from all over campus come, and I put up signs and I announced, hey, this really famous engineer here is here. Come on over. There'll be pizza and soda, and we can have a little get together and ask him or her about structural engineering and what their work is and all this kind of stuff. So again, that might be a critical live load case, because at that case, maybe that classroom is absolutely stuffed to the gills. Maybe we're going to completely ignore fire code and just shove 100 people into a classroom that normally seats 20 or 30. Maybe we'll shove 200 people in there. And so we get absolutely ridiculous live load. That might be your critical live load case. A critical wind load, at least here in Houston, I shouldn't need to tell you what this would be. This would be a hurricane, or maybe a tornado spawned by a hurricane. And so either of these could be this could cause a failure of the structure or a failure of the floor if it's not properly designed for it, and this can definitely cause failure as well. So the critical wind case would be the case where the wind is blowing the strongest, usually a hurricane. Critical seismic load, now we don't get this in Houston, but would be a largest expected earthquake. Earthquake. But back to the Houston example, yes, there may be times during a structure's life where it has a ridiculous live load, a critical live load more than it will at any other point, and there may be a time where there is a absolutely huge wind load in the form of a hurricane. But what are the odds that both of those are happening at the same time in the same place? I can tell you that if we're in the middle of an Category 5 hurricane, we're not going to have any sort of guest speakers coming in, packing classrooms with beyond fire code, etc. Those two things are not going to happen at the same time. Now, thankfully in Houston we don't have seismic, and then thankfully out in California you don't have hurricanes. But there actually are some areas where you can get both seismic and hurricane. Puerto Rico and some other Caribbean islands are examples of this. And so in those cases, you have to design buildings for both hurricane and seismic load, but you don't have to design them both at the same time. So your building must be able to withstand earthquake, it must be able to withstand hurricane, but it's a bit absurd to worry about that both happening at the same time. What are the odds that the earthquake of the century is going to strike at the same time as the storm of the century? It's yes, there is a non-zero chance of that happening, but it's so low. Again, if we design buildings for that, we would never be able to actually use them or afford to build them. So I'm not going to go down the exhaustive list of all load combinations, but these are found, I'm going to go through a few of them just to give you a feel for this, and these are found in ASCE 7. Or sorry, ASC 710. Or ASCE 7, not 710, just minimum design loads for buildings and other structures. So examples of load combinations. And just like we saw previously, we mentioned in the previous video, the exact load combinations you use will depend on what your industry is, depending on what your field is. If you're doing highway bridges, you'll use ASHTO. If you're using, and their load combinations, if you're doing buildings and basic structures, you'll be using ASCE. If you're doing offshore oil platforms, you'll be using American Petroleum Institute combinations, and on, etc. But let me just give you a few examples of basic load combinations. Basic combinations. The first one would be something like dead. Here. 1D. 2 then maybe D plus live. D plus live, dead and live, dead by itself, D plus L. Actually, this should be, I believe, 1.4 dead, if I remember correctly. 1.2 dead plus 1.6 live. My notes, I'm missing a little factor here. 1.2 dead plus 1.6 live. Then you might have D plus LR, and I may be missing a factor here. I need to check my notes on this. Or S or R. So you have to design for the dead. So here, this would be a case of critical live load. This would be a case where you have dead plus one of either roof live load, snow, or rain. Again, you pick one, or actually check for all of them. 2, or number 4, you might have D plus 0.75 L plus 0.75, 0.75 LR or R, or snow or rain. 5, you might have D plus 0.6 W plus 0.7 E. So a combination of wind and seismic, not the biggest earthquake. And so this is not the biggest earthquake and not the biggest storm, but the combination of a mild storm with a mild earthquake, et cetera, et cetera. And we can go down the list. But you notice you're generally always going to have D on here. You're always going to have dead load. And the reason for that is that, well, dead load is the structure's weight itself. Note, dead load is always present, is almost always present. Dead load is almost in all cases present. I need to check some of my numbers on here. I think in my notes I'm missing some factors. But anyway, so do check that against the ASC 7. And probably should have checked these before I started recording last night, but that's okay. Load is, sorry, I should put dead load is present in almost all load combinations. All load combinations. And how you work with these, basically, is you process. 1, calculate your nominal loads. 2, calculate all relevant load combinations. So you're gonna run through these calculations many times. You're gonna calculate this one, you're gonna calculate this one, you're gonna calculate this one, etc. Calculate all load combinations and design members for the largest, or what we call the critical. Design members for the largest load, largest combination. And again with this, as a reminder, these factored loads will ultimately produce your ultimate load. So it's going to be, you'll run through a whole series of load combinations, and whichever one is largest for a given member, that will be that one member's ultimate load, and that's what you design the member for. Okay, so I think that'll about do it for today. I think, sorry for this exceptionally long video. I know we went a bit over time, but hopefully you learned a few things, and it will be, and we can look at this and answer some questions in class. Okay, so again, that's the basic idea of LRFD philosophy. The key thing to keep in mind is risk. Remember that there is always going to be risk in a system. You can never eliminate risk entirely. In fact, let me just even give a few takeaways, final summaries. Parting thoughts. One, risk is extremely important in structural engineering. It must always be considered. There is always risk in the world. There's always variability and unknowns in both your strength and in your loads. And again, we have uncertainty in loads and uncertainty in capacity, strength, stiffness, that sort of thing. Capacity, strength, and stiffness. Capacity meaning strength and stiffness. And there are two approaches to control risk. And these are LRFD and ASD. ASD is more traditional, sort of a brute force method, although there is a science behind it as well. And it is not just it's not as a matter of simply, oh, just double everything. That's not obviously how we do it. And then LRFD, though, is a bit more scientific, and it will allow lighter structures, more efficient structures, etc. Also, again, I want to mention ASD is perfectly safe, just often overly conservative. It is safe, if a bit more conservative, if sometimes too conservative. It is imprecise in some cases, but it's imprecise in the direction of giving you extra capacity. Too conservative. And also keep in mind that load combinations are how you calculate LRFD ultimate load. The ultimate load for LRFD. In LRFD methods. Okay, I've reached the end of my slides, reached the end of my notes. I think it's time to go to bed. So anyway, we have the actual class, actual in-person structural analysis class bright and early tomorrow at 8 in the morning. So better get to bed. But anyway, I hope you enjoyed watching this video. I hope you learned a few things. This is, again, just a general overview of the philosophy behind risk, why we need to consider risk, the methods for considering risk, and how we can account for the unpredictable and vagaries of life, the universe, and everything via the methods of ASD and LRFD. All right, that'll do it. Let me know if you have any questions, and as always, thank you.